In this video, we are going to be determining the empirical and molecular formulas of compounds. Empirical formulas and molecular formulas are two different types of chemical formulas that communicate different information about compounds. Empirical formulas communicate the lowest whole number ratio of elements within a compound. Because ionic compounds are always reported as the lowest whole number ratio, the chemical formula for an ionic compound is always an empirical formula. Molecular formulas are used for molecular compounds. Molecular formulas specify the exact number of each type of atom present within one molecule, but they do not tell us how those atoms are connected. Molecular formulas are much more useful for molecular compounds, but we can also write empirical formulas for molecular compounds. Consider these two molecular compounds, benzene, C6H6, and acetylene, C2H2. For benzene, both subscripts are divisible by 6. C6H6 divided by 6 gives us an empirical formula of CH. For acetylene, both subscripts are divisible by 2. C2H2 divided by 2 is equal to CH. The empirical formula for acetylene is also CH. Both compounds have the same empirical formula, even though they are different compounds. Here's a practice problem. Write the empirical formulas for the following chemical formulas. H2O2. The subscripts are both divisible by 2. H2O2 divided by 2 is HO. The empirical formula is HO. N3O6. The subscripts are both divisible by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. The empirical formula is NO2. MgI2. The subscripts are 1 and 2. There is no common factor that can simplify these subscripts, so it is already in the lowest whole number ratio. The empirical formula is MgI2. C6H12O6. This is the chemical formula for glucose. All three subscripts are divisible by 6. Dividing each subscript by 6 gives us an empirical formula of CH2O. For our next one, we have C8H18. The greatest common factor between 8 and 18 is 2. Dividing both subscripts by 2 gives us an empirical formula of C4H9. There are many analytical instruments that can be used to determine the mass percent composition of a compound, including but not limited to atomic absorption spectroscopy, wavelength dispersive spectroscopy, and X-ray fluorescence. Our goal is to take this experimental data for mass percent composition and convert that information into a chemical formula. When doing this, we will be determining the empirical formula. Additional information would be needed to determine the molecular formula. Here's a helpful rhyme for remembering the steps to find the empirical formula. Percent to mass, mass to mole, divide by small, times till whole. Now, with this poem, not every step is needed for every problem. For example, if we are already given masses, we can skip the step for percent to mass. Or, if the subscripts are already whole numbers after dividing by the smallest value, we would not need to multiply to achieve whole numbers. This image shows the Cassini spacecraft, including a section labeled as a radioisotope thermoelectric generator, or RTG. RTG units are used to power spacecraft that are too far away from the sun to rely on solar panels. During graduate school, I researched thermoelectric materials that are used inside of radioisotope thermoelectric generators to convert heat into electricity, including a material made from ytterbium, antimony, and manganese. Here's some mass percent composition data that I collected during graduate school. Let's determine the chemical formula of this compound. Our first step is to convert percentages into masses. We will do this by assuming we have 100 grams of the compound. This allows us to remove the percent symbol and replace it with grams. This compound contains 35.39 grams of antimony, 63.86 grams of ytterbium, 1.448 grams of manganese. Our next step is to convert masses into moles. The subscripts in a chemical formula represent mole ratios, not mass ratios. We use the molar mass of each element as a conversion factor. After converting, we have 0.29065 moles of antimony and 0.36905 moles of ytterbium and 0.026356 moles of manganese. Now that we have our mole ratios, we need to divide by the smallest mole value. The smallest mole value is manganese. We will divide all three mole values by 0.026356 moles. This gives us a chemical formula of ytterbium 14.002, manganese 1, antimony 11.028. We divide by the smallest mole value to scale the smallest mole value to 1. Notice how the ytterbium and manganese values are already very close to whole numbers. The digit in the tens place is a 0. We can round. The empirical formula is ytterbium 14, manganese, antimony 11. In this example, we did not need our final step of the poem, times to whole, because we were already close to whole numbers. Sometimes after dividing by the smallest value, we obtain decimal values that correspond to common fractions. You are responsible for recognizing common fractions from 1/2 through 1/5. For example, if the subscript is 1.25, the decimal portion corresponds to 1/4. To convert this into a whole number, we would need to multiply all subscripts by 4. Another example is 1.333 is approximately 1 1/3. To convert that into a whole number, we need to multiply all subscripts by 3 to clear the denominator of a fraction. Remember that fractions are just division. If you are unsure of a fraction, you can enter it into your calculator to see what the decimal value is. For example, if you type in 3 divided by 5, you will see that it is 0.6. Here is another example problem. Vitamin C is 40.917% carbon, 4.578% hydrogen, and the remainder is oxygen. Because percentages must add to 100%, we can calculate the percent of oxygen by subtracting from 100. 100 minus 40.917 minus 4.578 gives us 54.505% oxygen. Now convert the percentages to masses by assuming we have 100 grams of compound. We have 40.917 grams of carbon, 4.578 grams of hydrogen, and 54.505 grams of oxygen. Using the molar masses, we can convert each of these masses into moles. We have 3.4066 moles of carbon, 4.541 moles of hydrogen, and 3.4067 moles of oxygen. Comparing all of these mole values, the smallest mole value is 3.4066. Dividing each of these values by that smallest mole value gives us 1 carbon, hydrogen 1.33318, and oxygen 1.00004. The carbon and oxygen are both approximately 1, and the hydrogen value is approximately 1 1/3. In order to clear the fraction on the hydrogen, we need to multiply the subscripts by 3. But we will need to multiply every subscript by 3 to keep things proportional. Our final empirical formula is C3H4O3. Here's a practice problem for you. Determine the empirical formula of hematite. Hematite contains 72.4% iron by mass, and the rest is oxygen. The molar masses are provided. You can tell that these are the molar masses from the units on the value, grams divided by moles. Your first step is to convert percentages into mass. Assume 100 grams of the compound. There are 72.4 grams of iron. The mass percent for oxygen can be found by doing 100 minus 72.4 to give you 27.6. Therefore, we have 27.6 grams of oxygen. Next, convert each of these masses into moles by dividing by the molar mass. 72.4 grams of iron is 1.296 moles of iron. 27.6 grams of oxygen is 1.725 moles of oxygen. Our tentative chemical formula is Fe 1.296, oxygen 1.725. Our next step is to divide by the smallest mole value, which corresponds to the iron. This simplifies to Fe1O1.33. The oxygen value is approximately 1 1/3. We will need to multiply both subscripts by 3 in order to clear the fraction and make it a whole number. We end up with an empirical formula of Fe3O4. Previously, we determined empirical formulas from mass percent composition. Now we need to determine the molecular formulas. Going from molecular formula to an empirical formula is straightforward because we can see the subscripts and simplify them. However, going from an empirical formula to a molecular formula requires additional information. For example, if the empirical formula is CH, we would not know whether the molecular formula is C2H2, C3H3, or C6H6. We need the molar mass of the actual compound to make our decision. The molecular formula is always a whole number multiple of the empirical formula. To determine the multiplier, we can use a ratio of the molar masses. We can take the molar mass of the molecular formula and divide it by the molar mass of the empirical formula to determine the multiplier. In this case, if we take the molar mass of benzene, which is 78.114 grams per mole, and divide it by the molar mass of the empirical formula, CH, which is 13.019 grams per mole, we can figure out the multiplier 6. This tells us that we would need to multiply the empirical formula by 6 in order to achieve the molecular formula C6H6. Here's a practice problem for you. Vitamin C has an empirical formula of C3H4O3 and a molar mass of 176.12 grams per mole. What is the molecular formula of vitamin C? Remember that the molecular formula is a whole number multiple of the empirical formula. We do not know whether the molecular formula is twice the empirical formula, or 3 times the empirical formula, or 4 times the empirical formula. However, whatever the correct molecular formula is, it would have a molar mass of 176.12 grams per mole. We could do a guess and check method to figure out what is the correct molecular formula. However, there is a smarter way of going about this. We can compare the molar mass of the empirical formula to the molar mass of the molecular formula. First, calculate the molar mass of the empirical formula. The molar mass of C3H4O3 is 88.062 grams per mole. If we divide the molar mass of vitamin C by the molar mass of the empirical formula, we find the molar mass of vitamin C is twice the molar mass of the empirical formula. This tells us that we need to multiply every subscript in the empirical formula by 2. The molecular formula of vitamin C is C6H12O6. We can always double check our answer by calculating the molar mass of this molecular formula and confirming that it matches the molar mass of the molecular formula provided in the problem.